difficult. Four times I'll start. So first I'll give a little bit of background introduction to what I'm trying to do. So the goal here is to construct examples of Pomerleano and infinity algebras which are smooth proper. So, such a thing gives rise to a TQFT by a theorem of 5 or 6 different people, I guess. And so the idea for how, like, the approach that I was going to take to do this is inspired by Dickerhoff. So the idea is visual duality. So what he proves is that, so social duality background here is that if you look at this category of modules, right, then these two algebras are cosine dual, and you have this object. The ground field, and what you do is you an endomorphism of the ground field. So
in the dimensional torus.
What? Yeah. Oh, no, it's grass matter. N-dimensional torus. Yeah. But here, so you get a cosine duality function, but it's not equivalent because this object C isn't a compact generator for this category. But what Dickerhoff proved, Dickerhoff, is that if you have a potential now, W here in the maximal ideal, then you take curve modules over this guy, and we further assume that something has an isolated singularity. So here, this is some deformed infinity structure. Which arises by calculating the end of C with itself, now in this category over here, the curved category. And so we're assuming here that W has an isolated singularity. Okay. So now the idea is maybe we can try to do something like this for other manifolds. Okay, so just we have to recall like a second, just a little bit of rational homotopy theory. So if you have M simply connected, because I'll use this dictionary a lot, so it's worth noting down. Then you have a Lie model, which is some DGLA or L infinity algebra, and the things to know about L are that the Chevrolet cochains on L are quasi-isomorphic to the cochains on M, and the other thing is that the universal enveloping algebra that is given by chains on omega of M again, the other thing to know about L is that the homology of L is isomorphic to pi star of omega m, where this is the Whitehead bracket. Okay, so what do you, if you look at these guys, so this situation, these are going to be our things we're going to try to play with. If you look at this, this has at least a formal resemblance to the situation where, you know, this thing is smooth but not compact. This thing is compact but not smooth. And here we have a similar situation that this guy is always smooth and this guy is always compact. So what we would like to do is in other situations to try to play the same game and consider some potential on this, and you know, and try to figure out when C is a compact generator. So the question is when is C a compact generator, and what is it? You know, that would automatically imply that well, assuming that the endomorphism leads to the vector space K isomorphic to this. Then that would imply the categories we would deform the category to become proper, and you know, assuming it stays smooth, then you might be able to produce an example of a smooth and proper Pomerleano this way. So Pomerleano category. So let's so here's an example. Example is when M is a product of even discrete counts. That it doesn't seem like such a big deal, but leads to a slightly different situation. So you have cochains. So let's look at what's the Lie model for this. So this is done n times. The Lie model for this is L over n, or one n of a generator so this is an odd degree. This is an even degree. And what we know is that the bracket of xi with xi is ui, and all the other brackets are 0. So if you look at the universal enveloping algebra, this is actually the Lie model. This is not, you know, this manifold is Lie formal, so this is actually the Lie model. And what you notice is that, so if you look at chains on omega of m, what you get are universal enveloping algebra is something like this. And so in the center of this is a polynomial ring, which is these guys. And the question is now, can we find a criterion, an explicit criterion when, so this now lies in the center of this guy, and the question is, can we find a criterion for when the category of models becomes smooth, proper, Pomerleano? And that criterion is exactly so here there's one subtlety, which is that you want to assume that the function is in this theory you want to assume the function is quasi-homogeneous or homogeneous, because there are some ideas for what a critical value, because otherwise you might have different critical values of your function. There's some idea of what, like, I guess in the paper with Pantev, Katsukov, and Katsevich, there's some idea of like what critical points should be in this situation, but I've kind of avoided that. So we're going to assume that. So this corresponds to avoiding that. So we're going to assume that the polynomial is quasi-homogeneous. And then in that case, what you get is that you have this criterion, which is that it's not that the Jacobian ring should be bidirectional, it's that this thing should be bidirectional. So what is this about? Well, if you look at this geometrically, what this is really telling you is that your function, not just that your function should have isolated critical points, but that your function should have isolated critical points restricted to all the coordinate axes and their intersections. So so where does this come from? I mean, so the new ingredient to proving things like this, so in the Lie formal setting is like it's some non-commutative algebra. So where does it come into play? Well, it comes in the way that this condition comes into play is basically if you have what you have is you have because of the structure of this Lie algebra you have basically get a bilinear form, which in this case, from the map from B odd, tensor B odd to B even, and what that correspond looks like is it's like this, and this is the discriminant locus of that form, and so it comes into the non-commutative algebra when you try to mimic the proofs that of given by Dicker-Hoff and other people that use the generator. So another example would be like in the same vein would be a cochange design. So here's a non-formal example would be this is non-formal, at least in the infinity sense. So it's Lie formal. So you have E1 equals 2. And here, what you have is so the it's something 6-dimensional manifold, I think. They're really not the top of my head. But yeah. So all these. So what the form looks like is E1. And again here. Yeah, so again here, if you take a homogeneous polynomial and variables and you restrict to the discriminant locus, which is where this thing vanishes, this determinant vanishes. So so the condition is exactly the function has isolated singularities and that its restriction to that locus has isolated singularities. Okay. So what this suggests is that the right set of manifolds to look at for this question are exactly manifolds that look like this in some way. So that class is called the pure Sullivan algebras. And if you have the pure Sullivan algebras are exactly things. Let's just C star of M are relative to the X and DK and DE I equals to Fi and dx j equals to 0. So they're things like this, and the reason that this class is interesting to look at are because if you consider the Lie universal, if you consider the Lie model, it has a large abelian part coming from those variables. So you always have a map from an abelian Lie algebra an even degree to your pi lower star of L of M of omega M. Right? This should be L, the Lie model, and you always have such a map, and that gives you a map from the polynomial ring. So you always have at least if you pass to a minimal model over here. And this guy's always finite over this ring. But this might be some now has some A-infinity structure. But unfortunately, I don't really. So the techniques I'm using to try and tackle these cases are non-commutative algebra techniques. I don't really have a good way to prove the generation in this case, but I can write down a criterion for when so this is the conjecture part. So I don't really have the right A-infinity non-commutative algebra to handle the non-Lie formal case. But you can write down the conditions pretty easily by considering. So this has a nice form, and you can look at what you can write down the Hofschild cohomology. And yes, you can write down this. You can write down. So you have polyvector fields on this algebra, and this differential gives you a bracket. And what you can show is that the polyvector fields of this bracket, you can modify Konsevich's formality maps to show that this covers the deformation theory of this pure Sullivan algebra, and so you can show that the classes basically that we're interested in doing the deformations are polynomials in these DEI. So we have W in here, a polynomial. Yeah. There's W in here, and then the deformed Hofschild cohomology should be T poly of V plus WT and T poly T. And then the claim is that if this is finite when you invert T, then at least in all the examples that we have so far, that corresponds to the category means movement, the cosal duality, so some kind of deformed cosal duality. And so this deformed algebra becomes Oh, okay. So higher category interpretation of these deformations. So we have Seidel's picture that the compactification corresponds to deformations, and so if you want to understand when it is that the mirror, if you have the mirror of Pn, well, that's just given by so there's if you look at the root stack on the toric divisors, what the mirror for this, if you let those guys come with parameter AI, then the mirror becomes exactly x to the n. X to the a0 an with the same relation. And so similarly in this picture now, if you have the anti-diagonal embedded inside of the P1 times P1, And the diagonal basically the compactification of the cotangent bundle. And if you basically put a root stack structure on that diagonal, and you could compute a deformed floor cohomology, then what you get is exactly so this is the simplest case. This is for S2. You get exactly so change on omega m for S2 is exactly going to be something like this, and then if you put a d degree for the root for the d ramification on that diagonal, you get exactly the endomorphism of C for this potential. So I guess I'm now done, but sorry if that was entirely unclear, but I kind of wanted to get that in. So any questions? WT. It depends on if you right. I mean all the, if you just WT.
More questions? How big or small is the category of models for your Calabi-Yau algebras? For instance, how big is K0?
No, I've never done that calculation. I probably could do it for like this pretty simple example. But this is it's a little bit different because you're this guy being odd makes it a little different than the usual case. In fact, it's an odd variable instead of an even one. Makes it a little bit different.
So somehow you calculated here you said that that polyvector field thing should be somehow quasi-isomorphic to some function cohomology of
Right. This
but is this the usual function cohomology or some?
well, this is now for the this is for the causal dual. This is for the pure Sullivan algebra itself, not chains on omega n. So you don't have to do any kind of completion on the causal dual side.
All right. So it's not for the curved algebra. It's for
Right.
the causal dual.
Right.
Turn over the question.